Well, thank you very much for me being here. I want to emphasize the very great explanatory power of the time-extended paradigm, where past, present, and future are extended all at once. This paradigm was used very early in the extremum principles of Fermat and of Maupertuis. But of course it has its full extension in the relativity theory, where what is essential is the metric of space-time, which has been discovered by Poincaré and very much used by Minkowski. What is surprising is that this time-extended paradigm fits extremely well with the probability calculus. This at first sight seems surprising, but it is very true. This is proved by the fact that the Feynman probability calculus is expressed as a probability calculus in space-time. So you see that the space-time paradigm is definitely not committed with a deterministic view of the world. This Feynman wave-like probability calculus is pictured geometrically in space-time or the momentum energy space, not in both, of course, at the quantum level because of the Heisenberg uncertainties. An algebra is behind it. It is the one which has been discovered in 1926 by Born and by Jordan. It is a wave-like algebra of probability, and it has been cast by Dirac in the form of a very efficient symbolic calculus. Since a few months, it occurred to me, when investigated together the EPR correlations, either proper or reversed, and Wheeler's smoky dragon metaphor, that Laplace's 1774 conditional probability calculus can be recast in a form strictly paralleling the Born-Jordan-Dirac transition amplitudes calculus. And thus is this classical calculus of probabilities is also picturable in a relativistically covariant way. With in the Feynman scheme, conditional probability or amplitudes are used, and in the classical one, of course, in the Feynman scheme, it is conditional probability and amplitudes that are used, and in the classical case, it is conditional probabilities and that are used. The two words, transition probability and conditional probability, or amplitude, are strictly equivalent to each other and can be exchanged. Not only time extendedness, but also past-future symmetry is a basic trait in all this, of course, already in the extremum principles of Fermat and of Maupertuis. And this also comes as a surprise in the probability calculus. All physical theories, including the probability calculus, have displayed this past-future symmetry. And here I must discard a very widespread prejudice. Such loose statements as physical irreversibility is easily explained on a probabilistic basis are completely misleading, as they tacitly equate probabilistic reasoning with predictive probabilistic reasoning, and thus they beg the question. In fact, independently, both Laplace in 1774 and in later years, and also Boltzmann have devoted second thoughts to the question and have clarified it in depth. To this I will come back. Intrinsically speaking, statistical prediction and statistical retrodiction are exactly symmetric to each other. As an example of blind statistical retrodiction in physics, I can give the Heisenberg microscope thought experiment. In that experiment, you have in the object plane of a microscope, you have an electron which diffuses a photon which is received in the image plane of the microscope, where it has a punctual impact, and from there you do a blind statistical retrodiction. That is, you think of the light going backwards, or else you imagine that this point in the image plane of the microscope is a little source, and you have a wave going back, and then you have a diffraction pattern in the object plane of the microscope, and from this you discuss where the electron was, and also using the aperture of the microscope you discuss about the momentum. So this Heisenberg microscope thought experiment is a very neat example of a blind retrodiction in statistical retrodiction in physics. Fact-like asymmetry between predictive and retrodictive probabilities, if any, rests entirely on inequality between the prior probabilities of the initial and of the final states. Could I please have the first picture? Please, can I have the top of the... So this is recasting Laplace's algebra of conditional probabilities, and I use the following definitions and notations. What I use is the joint probability, which I write this way. Okay, problem. What can I do? Okay. The concepts I use are the joint probability, which I write this way, intrinsic conditional probability, which I write this way, two extrinsic reciprocal conditional probabilities, which I note this way. These are the ones used since the days of Laplace, and the prior probabilities of the two occurrences which are at stake, and also in view of the following, what I call background probabilities. Now the formulas, could you please move a little bit? Do you hear like that? Do you hear? Okay, it works. Okay. So, for the formulas. Formula 1 is reversibility of the intrinsic conditional probabilities. It was Laplace's 1774 assumption. Formulas 2 are merely computational rules. You can skip over them. Formulas 3 are the definition of the two reverse extrinsic conditional probabilities. Why I call them extrinsic? It is because they contain the prior probabilities of one and of the other of the two occurrences which are at stake. Formula 4 is a very important one. It expresses the joint probability of two occurrences A and B as the product of three independent probabilities. That is the intrinsic conditional probability and the two prior probabilities of the occurrences at stake. Using the line above, line number 3, this can be recast in the forms which you see here and here, which are those which are very well known since the days of Laplace. That is, the joint probability is expressed as the product of the extrinsic conditional probability of A if B by the prior probability of B, or also as the extrinsic probability of B if A multiplied by the prior probability of A. If you set B equal A in the formula above, you get formula 4 prime, which shows three things. First, it shows that the intrinsic conditional probability of A if A equals 1. Looking at the line above, it shows that the extrinsic conditional probability of A if A equals the prior probability of A, and this is very well known since the days of Laplace. It also shows that this expression, that is the joint probability of A if A, is a projector. So this allows orthonormalization according to this. Could you please move the thing? Thank you very much. And now I speak briefly of the way both Laplace and Boltzmann independently have discussed facts like irreversibility. The theorem is the following one. The necessary and sufficient condition for the two reciprocal extrinsic conditional probabilities to be equal to each other is that the prior probabilities of A and of B are equal to each other. Maximal irreversibility is obtained if all B's are equal among themselves, so that there is no need to mention them. And this is what independently Laplace and Boltzmann did. Now I change the subject. I go to formula 7, which is the generating formula of Markov chains, you see, with a summation over intermediate states. But intermediate is understood only in the algebraic fashion. No geometry nor timing implied here. All this is an algebra, so there is no timing at all in it. This is a complete Markov chain. And now I speak of the end prior probabilities, those here, A and del. It is well known in the Bayesian approach to probabilities that the end prior probabilities are shorthand notations for background conditional probabilities connecting the system with the environment. You see, the end prior probabilities are background notations for these things where E and E prime express probabilities pertaining to the environment, background information. Could you please move slightly there? You can see, okay. So now I insist that the two concepts of conditional and transition probability are strictly equivalent to each other and thus can be exchanged. The transition in the word transition probability is between two representations of the system with absolutely no timing involved at this stage. Could I now have the next slide, if you please? Now, this is the Born-Jordan-Dirac algebra with wave-like amplitudes. As you will see, it completely parallels the other scheme, but we had amplitudes instead of probabilities. So, as before, I consider the joint amplitude written this way, intrinsic conditional amplitude here, extrinsic conditional amplitude, there are two of them here, higher amplitudes, and background amplitudes. Formulas. Formula 1, as before, expresses reversibility of the intrinsic conditional or transition amplitude. It is Hermitian conjugation. These are computational rules. We can skip over this because it is very seldom used in quantum mechanics. And here we come to the definition of the joint amplitude, which is written here as the product of three independent amplitudes, the intrinsic condition or transition amplitude and the two end prior amplitudes. It can be written this way also. And as before, if we set B equal A, we find that this is a projector, that the intrinsic conditional amplitude of A with given A is 1, and that the extrinsic one is equal to the prior amplitude of A, and that this is a projector. So we can have auto-normalization. Formalization or reversibility, I skip over this because it's similar, a little more complicated. Instead of Markov chains, we have Landé chains working with amplitudes here, which, as is well known, are generalized as Feynman graphs. Here we have a complete Landé chain, and here the end prior amplitudes are also shorthand notations for conditional amplitudes connecting the system with the environment. And here you recognize very well something which is used by Dirac. You know, Dirac considers a set of state vectors, functions of x, which are labeled by an index A, and he shows that these can be understood as transition amplitudes between two representations, the x1 and the a1, similar in momentum energy space. So you see the two algebras are strictly parallel to each other. However, they are not superposable because of the famous Born-Jordan 1926 formula expressing the conditional amplitude probability in terms of the conditional amplitude. Please remember this formula omega. This formula contains off-diagonal terms. That it is from these that proceed almost all paradoxes of the quantum theory, including a consequence of these off-diagonal terms, which are interference-like. And these consequences are termed non-separability when thought of algebraically, and are termed non-locality when they are displayed geometrically. Well, thank you very much. All these definitions are basically timeless. For example, a transition is between two representations of a system, that's all. The two algebras correspond to each other. The Laplacian one uses addition of partial probabilities and multiplication of independent probabilities, whereas the Born-Jordan algebra uses the same thing with amplitudes. Therefore, while the classical intermediate summations, and I insist that intermediate is meant algebraically, nothing else, summations are over real hidden states classically, in the quantum case they can no more be thought of as over real hidden states, and they are said to be over virtual states. When a space-time connotation is attached to the chance occurrences A, B, C, etc., quantum non-separability is termed quantum non-locality. And then also, when we speak in terms of geometry, the transition amplitudes are termed wave-like propagators. Thus, in quantum mechanics, law-like reversibility of waves and law-like reversibility of probabilities go hand in hand, and so do also fact-like irreversibility of waves and fact-like irreversibility of probabilities. And here I recall a very famous Ritz-Einstein controversy where this matter was at stake. Due to the Laplacian or Hermitian symmetries, which I have explained, a Markov chain and a Landé chain can zigzag arbitrarily throughout space-time or through the momentum energy space, completely disregarding the macroscopic time arrow or energy arrow. This is topological invariance of Markov chains and of Lambda chains, and also of Feynman graphs, where it is very well known. Now I give some examples. First, an example showing how we can use a timeless concept of probability. The number of male US citizens having a height h and a weight w is the joint number of chances of h and w. And also, in the absence of prior probabilities of h and w, it is also the intrinsic conditional probability that of h if w or of w if h. But now, if the subclasses of, say, weightlifters or basketball players are at stake, then the prior probabilities of h and w must make sense, and the joint number of chances then is reduced accordingly. Basketball players are usually tall and light. Therefore, the prior probabilities of high values of h, the height, and of w, the weight, are v1 very big and the other very small. Therefore, the Laplacian or extrinsic conditional probability of h if w is much larger than the extrinsic conditional probability of w if h. This is logical irreversibility. It has nothing to do with time. Now I give an example of topological invariance of Markov chains. This entails that in space-time or in the momentum energy space, an ABC zigzag can have a V shape or a lambda shape or a C shape. For example, in a national park, we can ask what is the joint probability that the male bear of a couple is present at M and the female bear at F, the MF vector being either space-like or future time-like or past time-like, it does not matter. Coupling implies interaction, and this means that the two bears can meet at some real hidden place, P. The MPF zigzag having either a V shape or a lambda shape or a C shape. Logically speaking, this makes absolutely no difference and the formula is not changed at all. Summation is needed over the hidden states P, which are termed intermediate only in a topological or algebraic sense, completely disregarding any timing implication. Topological invariance of lambda chains and of Feynman graphs entails that an ABC zigzag can have a V shape or a lambda shape or a C shape, either in space-time or the momentum energy space, but of course not in both at the quantum level. A V-shaped ABC zigzag figures an EPR correlation proper. A lambda-shaped ABC zigzag figures a reversed EPR correlation, whereas a C-shaped ABC zigzag illustrates the concept of Wheeler's smoky dragon. In all three cases, the intermediate summation at B is over virtual states, not over real hidden states. An EPR correlation proper is between two distant measurements A and C issuing from a common preparation B. The states at A and B should be said virtual as thought of in terms of the two Hilbert spaces of A and C. However, in the product Hilbert space, the B state is a pure state. For example, it is a spin zero state in the now famous cascade experiments. A reversed EPR correlation is between two distant preparations merging into a common measurement. The comment mirrors in time the preceding one, so I do not speak anymore of it. Wheeler's smoky dragon is a quantum system B which is evolving between its preparation as A and its measurement as C. As it is actually transiting between A and C, it is neither in the retarded state generated as E nor in the advanced state absorbed as C. It is in a superposition of states of the Hilbert spaces of A and C. However, in the joint Hilbert space of A and C, it is in a pure state. That is, it is in the state of the virtual particle which, interfering with the system between A and C, would wash out the difference between A and C. So, the evolving system is not in a state. The concept of an evolving state vector is obsolete, just as obsolete as was the late luminiferous ether. It is very well known that if one tries to use the concept of an evolving state vector, one gets very easily into trouble with Lorentz invariance or with CPT invariance. Only the transition amplitude concept does make sense. So on the whole, we have three smoky dragons. We have Wheeler's smoky dragon, of course, and we have also a smoky dragon in the source of an EPR correlation, and we have a smoky dragon in the sink of a reversed EPR correlation. in this conditional amplitudes concept calculus, what counts is the setting of the preparing and measuring devices while the particles go through. What these settings are before or after is completely irrelevant. And this has been felt as very paradoxical in the EPR correlations proper, whereas it is perfectly evident in the formula. However, it is quite trivial in the reversed EPR correlation. This has to do with causality. And indeed, it binds tightly together the two concepts of causality and of conditional probability or amplitude. In fact, I think that physically speaking, there is absolutely no difference between the causality concept and the conditional probability or the conditional amplitude concept. The conditional amplitude formula holds if and only if each and every partial measurement and if each and every partial preparation as written down in the formula is performed. Could we please put this slide on? Causality has any operational meaning. It implies that something can be arbitrarily adjusted at some place and time. Deciding if the consequences appear later or earlier is a matter not of metaphysics but of physics. And in the EPR correlations proper or reversed, and in the Wheeler-Smokey Dragon concept, we have adjustable parameters at A and C only, not at B. Then just look at the implications. You see, look at this picture. You see, these are not space-time diagrams. They are symbolic drawings. Well, here, we look at this one. This is the EPR correlation proper, and this is the reverse EPR correlation. In the EPR, do you hear like that? In the EPR correlation proper, we have at B a source with two particles going out. Say we have a spin zero system, and we have two photons going through these two linear polarizers and received in these two absorbers. We can think as these two linear polarizers as crystals, birefringent crystals, that is, they yield the two possible answers. Similarly here, we have two lasers and two light beams of very low intensity going through two linear polarizers, and the two photons can be absorbed in an anti-cascade here. And if we think retrodictively, the cascade being assumed to go on, the calculation is exactly symmetric to the predictive calculation with the EPR correlation proper. And here we have the Wheeler-Smokey Dragon. We have a laser, low intensity laser, shooting through a linear polarizer, and the light beam is received through another linear polarizer and absorbed here. And here in between, we can have a birefringent crystal, the length of which is such that no phase shift is introduced. So we cannot decide experimentally, and it is forbidden to think of each photon traversing this crystal that it is on one of the two possible beams or the other. This is exactly the Smokey Dragon concept. We can, as no measurement is performed here, we can know nothing, and we are allowed not to think at all of what's good, or not to think in terms of a photon in one state or the other. This crystal can be turned arbitrarily, and this shows the possible change in coordinates of this intermediate state B. Now, what has been, can we go back please to the, in the reverse EPR correlation, everybody accepts quite easily that once the photons have gone through the polarizers, we can turn them arbitrarily. Everybody understands that this will not change the result. This is because people think in terms of retarded causality. They think that once the photon has acquired the polarization here, it conserves it until absorption here. Whereas in the reverse EPR correlation, you get into trouble if you think in terms of retarded causality. And the people were very upset to see that you could wait until the very last moment to turn the polarizers here. In fact, the formula shows that what counts is only the orientation of the polarizer while the photon goes through. So here, the reverse EPR correlation displays retarded causality, and the EPR correlation proper displays advanced causality. But in fact, these are mainly two aspects, because basically the causality concept is time reversible, or should I say more precisely, if I have time to go it, should be said CPT invariant. So, conclusion. At the elementary level, causality is time reversible. This was already implied in the 1874 Loschmidt paradox. This paradox really showed that causality is time reversible. But the point is made much more dramatically with the wave-like probability calculus than it was done with the classical probability calculus. Now I come to an important point. If picturable in space-time, a probability calculus cannot have a statistical frequency interpretation because there is only one world history. Thus, to think consistently, one must go back to the concept of probability that was used by the early proponents, that is Bernoulli and Laplace, and which is now used by E.T. James. That is, probability is very much a subjective concept. It speaks of what we think or what we can do upon a system. Of course, we can do statistical experimentation, but not on the whole of space-time, only in parts of space-time during repetitions of an experiment. But this is working only with small pieces of space-time. If we think of space-time as a whole, we cannot use the frequency concept of probability. The crucial point here is evaluation of the prior probabilities, which, as I will show, is a matter not only of cognitive information, but also of organizing information. And this opens radically new vistas. But before I go to this, let it be emphasized that not only the twin concepts of probability and of information, but also the very space-time concept should be said neither objective nor subjective, because they are indissolubly both. They have, so to speak, one foot in Popper's and Haeckel's world one, that is the world of the things we see around us, and they have in foot in world two of Popper and Haeckel's, that is the representation world in our minds, inside our mind, inside, so to speak, our minds. Why space-time loses in quantum mechanics the objectivity it was thought to have in classical theory is because the Heisenberg uncertainties forbid us to use simultaneously the xt and the momentum energy representation. In world one, there are sinks of negentropy, which are sources of information as knowledge in world two. In the quantal jargon, these are termed measurements. But ignored by the much too radical irreversibility statements due to Sadi-Carnot, to Laplace and to Boltzmann, there are also sources, in world one, there are also sources of negentropy, which in world two are sinks of information as organizing power, which are termed preparations in the quantum jargon. Physical irreversibility, which is fact-like, does not mean suppression, but it does mean repression, merely repression of advanced actions and of decreasing probabilities. And again, expectation of these end probabilities is expressed as an evaluation of the end prior probabilities. In the quantal jargon, these end probabilities are the initial occupation numbers of the initial states and the final occupation numbers of the final states, either in the Bose or in the Fermi statistics, where these occupation numbers appear symmetrically. These occupation numbers are thought of as being there either in space-time or in the momentum energy space. This I can make clear by using a comparison. Suppose that in ordinary space we have a network of phone cabins connected to each other. The traffic on a line is a product of the channel capacity by the occupation rates of the cabins, the occupation numbers of the cabins, so to speak, and all this is thought of as being there in space. Well, similarly, if you use, say, the S-matrix calculation, the end prior probabilities, that is the occupation numbers, are thought of as being there in space-time or in the momentum energy space. Topological invariance in space-time of the conditional or transition probabilities is tantamount to reversibility of the information to negentropy transition. That is tantamount to the law-like equivalence of information as gain in knowledge and of information as organizing power. And now let me quote Wigner. Wigner, in his book Symmetries and Reflections, after symmetry arguments very similar to the ones I have used here, comes to this statement. Wigner says that to every action we know that there corresponds a reaction. Therefore, says Wigner, to the action of matter upon mind, which is gain in knowledge, there should correspond the direct action of mind upon matter. Wigner doesn't give any name to that, but the name is quite obvious. It is termed psychokinesis. do we have experimental evidence of psychokinesis? Well, here in my hands, I have the photocopy of the galley proofs of an article by Sir John Eccles, Nobel Prize winner. This article is in press at the Proceedings of the Royal Society of London, and the title of the paper is "Do Mental Events Cause Neural Events Analogously to the Probability Fields of Quantum Mechanics?" And the object of the article is that Eccles says that having done neurological experiments with the human brain, he has demonstrated that at the root of voluntary action, you see when I raise this piece of wood here, there is a biasing of the natural predictive probabilities. That is, we must not take all the n prior probabilities equal to each other. That means that we are using partly blind statistical retroduction, which of course is equivalent to using probability backwards in time. That is also equivalent to advanced actions. Therefore, I have discussed the matter with Eccles, which I have met in a meeting recently, and I said what you are saying is in fact that voluntary action is psychokinesis inside our brains, and he said this is exactly what I'm saying. And he went on saying, well, I truly believe that something similar must occur in biological phylogenesis. And then I pointed to Eccles that somebody before him had said the same thing, and quite surprisingly, this man is Descartes. Descartes, in 2 letters, one to Arnaud, who was somebody of the days, and one to the Princess Christine, says this: we know by internal experience that our voluntary action is direct action of our will upon matter, and this is shown to us in everyday experience and cannot be discarded by any ratiocination or argumentation of any kind. You see, the argument is exactly similar to the one of the cogito. Descartes says here that we have internal experimental evidence that our will moves our body, and he goes on saying it is not at all the same thing as when a billiard ball hits another billiard ball. And in the other letter he says we must be careful not to use concepts inside the realm where they are valid, and for example we must not at all think of the action of our mind upon matter in the same way as we think of the action of matter upon matter. Okay, so above this, in the quantum wave-like probability calculus, there comes in non-separability, as I have said. That is, in geometrical terms, non-locality. This means direct long-range connection, both space-like and time-like, and arrow-less, which are arrow-less in time. This, together with use of a Bayesian or Laplacian probability concept, makes a worldview where intersubjectivity should replace objectivity. It is a Maya sort of world, the non-solidity of which is demonstrated by the happily rare occurrences of the so-called paranormal phenomena. Well, I have a postscriptum pertaining to CPT invariance, but I think this is a technical physical point. I think I need not go into this here. So thank you very much for your attention.